Greetings. This is Ramesh Gulati. Good morning, good evening, good afternoon, wherever you are. Greetings from the Music City, Nashville, Tennessee. I'm Ramesh Gulati, your host today. And today we're going to talk about calculating and specifying reliability to improve uptime and availability. With that, let's start. Uh, this is kind of my outline today of my talk. We're going to talk about safety minutes, introduction, knowledge assessment, sort of a understanding key reliability terms, and how to calculate specified reliability, and then takeaways and conclusion. Safety. Over the years, what I've learned that safety and reliability go hand in hand. As you become reliable, you become safer, and as you become safer, you become reliable. We're going to talk about that. So always I start a meeting like this with a safety moment. Usually I ask my participant to talk. Again, this is a webinar, so it's kind of, I'm going to take the opportunity here to discuss what I think is important. And one of the things we're going to talk about is ladder safety. Ladder safety has been one of the top five incidents in OSHA's last few years, the top five. So here's the question. What should be the safest distance of the ladder from the building at the base should be? How much that should be from the base? Is A, 4 feet, B, 6 feet, or 1/5 of the ladder's length, or 1/4 of the ladder's working length? What do you think, guys? Well, it should be one fourth, 1/4 of the height. Okay, so if you got a, if it's a 12 feet distance, so it should be 3 feet from the base. Again, these are kind of some of the things we should be careful. Use 1/4 rule on placing the ladders from the wall. Use both hand climbing, 1% at a time. Please follow the right instructions how to put a ladder, use a ladder properly. This is about me. I've been around for many years, over 60 years in the business. I started working as a maintenance engineer when I graduated back in 1963. And since then, I've been working. I retired a few times, and now I'm working with ReliabilityX, my friend over there. And again, it's a passion to teach, talk to my friends, and help everyone. And they call me Reliability Sherpa. And in my spare time, I've written a few books. Hope you will read it and enjoy reading. Let me know how you do. Okay. With that, let me again. I ask in a regular class who you are, but this is a webinar, so it's very difficult to ask. I don't know who are there where. Okay. So I'm going to skip this part. Now, I'm going to spend a little bit time. You guys should spend a little bit time on this screen. What's the best way to improve reliability? Is it with a good maintenance plan? True or false? List three mean metrics you have used or you have heard. And if an third question is if an asset or pump operated for 100 hours and have five failures and took 10 hours to repair those five failures, what is the mean time between failure for this asset? Now, question number four is the same question as in question three. What would be the mean time to repair for this example? The fifth question is if an asset motor unit has a reliability of 90% in 10 hours of operation, what does that mean? If somebody says I have 90% reliability, what that mean? Okay, so you can write down your answers, and I'm going to go through one by one to give you answers for these questions. Question number one, best way to improve reliability is with a good maintenance plan. It's false. It's not true. Many people think that with the maintenance plan, we're going to improve reliability. We're not. We are sustaining the reliability with the maintenance plan. To improve reliability, you have to make changes in your design. You have to bring new parts, new components, those kind of things. You have to kind of redesign. Maintenance, what it does, it sustain the reliability, what is built in, what comes with the when you buy equipment that time with your asset, that's got inherent reliability that's built in. That's what you are trying to sustain that reliability of that. Three mean metrics: mean time to between failures, MTBF, mean time repair, mean downtime. These are kind of three commonly used three key metrics. Mean time between maintenance actions and there are few others there too. If an asset operates 100 hours and 5 failures, it took 10 hours to repair. What is the mean time between failure? You take operating time, 100 hours, divide by number of failures, in case 5. So our is at 20 hours of mean time between failures. Question number 4, what's the mean time to repair? It took 10 hours to repair 5 failures, so our mean time repair is 2 hours. If an asset motor unit has reliability 90% 10 hours, what does it mean? It means that there's 10% chance of failure in a shift of 10. Whatever your shift have 10 hours of operation, and in that there's a 10% chances of failure. That's what it means. What is reliability? What does reliability mean to you? If somebody says reliability, what it means comes to your mind, your head. Okay. You know, reliability is a quality of being trustworthy, performing consistently well with no or minimum failures. When we're talking reliability, reliability really is a probability function. It's a likelihood of mission success. And what is a function? Are you heating something, you're cooling, rotating, providing some function, or motor like a pump? It has so many gallons of water or fluid, hydraulic fluid. We want a certain pressure. That's a function. And we need to, when you're talking reliability, satisfactorily, do that function. And then also, it has a specific period of time, 5 hours, 10 hours, 50 hours, 100 hours, so many number of cycles, so on and so forth. And what's the operating conditions, temperature, pressure of outside, inside, those are kind of things. Because certain equipment are designed to operate in certain environment. So that's, designer had designed that in mind. So when we are talking reliability, it's a probability function. And to perform certain function satisfactorily under specified conditions to a specific period of time. Is that reliability? So it's a lot of things in it. So reliability is, some people, you go to a university, take a few classes, mug up all those formulas. Is that reliability you calculate? Or on your machine, there's a reliability button. You press that and you get high reliability. Or this picture, I'm showing you a technician is waiting for that call so that he's a service technician waiting for that call to come. So go and repair that. That call never comes. He's sitting there, kind of sleeping in this case, is extreme case where we are trying to show. In fact, this was one of the ad came back in 80s, were pretty common with the Maytag dishwasher and washers. So that's again, if you think about what that means, that is really peace of mind. Reliability gives you a peace of mind. Things are working they're supposed to work. They're working the way they're supposed to work. And there are no failures. And that's what reliability is. Peace of mind. Everything's working the way it's supposed to work. No failure or minimum failure. Who owns the reliability? In your place, is maintenance owns it, or operation owns it, production owns it, or designer, if they're there. Or is it a quality or procurement guys, or store guys, or is it HR who provides the people and training and those funding for those, or the management? Who owns the reliability? Think about that. Right now, something. You know, yes, maintenance may own it partly. Operation, yes, definitely they own it because they operate those assets. Maintenance supports it, do the preventive maintenance, those kind of things on assets. Engineering, yes, they get the design done on those. Definitely they own piece of the pie. Purchasing, they buy those equipment and components, and sometimes they're responsible for storing the component parts also. Finance, yeah, they provide the funding for that, or funding for your whole operations. Management, yes, they're partly responsible because they provide the leadership support kind of thing. Yes, it's a owns by everyone in the organization. Anybody who touches in somewhere from concept all the way as it is operating, they have a stake in their shareholder. Where do defects get introduced? If failure happens, those defects get introduced somewhere in the process when asset is being designed or bought or brought or is being designed or is being specified or is being installed or commissioned, and then it's operation and maintenance and improvements capital project. Where do defects get introduced? Think about that. You know, they say operations. Yes. If we don't train our people, operators, or tell them how to operate these machines properly, we don't train them. Yes. And there's a data showing that 40% or more failures are due to are in operation when people are operating it. Again, most of the time, lack of training, lack of understanding how to operate them properly. Maintenance, yes, they have to maintain them. And if we don't provide them right tools, right training, yes, they may not repair them properly. They can create a defect, they introduce something so the failure happens. Design, definitely. A lot of our problem, what we see a lot of time when as a machine was not designed properly, not with this proper component. Again, it could be their fault, designer, or they didn't get the proper funding to specify right components, high reliable component, all those kind of things. Procurement, yes, they may not provide the right funding, or they might go buy for the cheapest component, cheaper machinery. They should be buying for the best value. That's what they have to do. Manufacturers also who building it, that asset, may not build with the right people, with the right skill set, or may not use right components, what was specified or whatever. They can cause a problem. Or installation commissioning, yes, if you don't install them properly, if the alignment is not right, or there are few things are we found it, they don't change it or do something there. That can cause a problem. Stores storing the parts, machines. If we don't do things right, yes, it can damage. Yes, there's a lot of places. Every place defects get introduced, which we see as a failure while we're operating that machine. Finance management. Yes, all of them are responsible, or they introduce some kind of defect which we see as a failure when we operate those machines. HR, human resources, if you don't provide right training or right training or right funding. Okay. So at everywhere, mostly design, operation, procurement stores, where defect gets introduced means something we don't do right there, and that we see in while assets being operated. Now, this is just a few examples. Operation improper planning, misuse of equipment, poor procedures, maintenance, inappropriate maintenance practices, poor workmanship, lack of skills and training and tools, engineering, improper design, undocumented changes, management, poor management policies, lack of resources, procurement, wrong parts, late deliveries, poor vendor selections, sales marketing also, they give a unrealistic delivery commitments. And as a result, hey, we have to hurry up. Operation production try to make more parts which may be beyond capability of that machines, and they fail. All those kind of things happens. So everyone owns the reliability in this food chain. Now, another question is, what percent of reliability do we need? Do we need 100%, 99%, 90%, 50, or what? Think about this. Think about what reliability can afford. Yes, I want 100% reliability. How much is it going to cost you? Or do you need it 100%? Yes. If somebody don't opt in operating theater in the hospital on me, my heart, I want 100% reliability or 99.999. Yes, it's important. But if the light bulb in a bathroom, fan or something, which is not that important, I can live with a 50%, 80%, 60%, 70%. So it depends, it varies. Depends for your need. You need whatever percentage of reliability you need. You know, most of reliability when we talk about bathtub curve, which is very common. And human being, we also kind of follows bathtub curve, where as asset comes, there is infant mortality part, where as initially there's some components are not right or whatever defect at that period maybe it depends upon is there a few hours, few days, uh, a few weeks depending on the complexity of the asset. And once that's over, then we go in a constant failure rate. That's random and random failure rates. That's in the center. That's what is a useful life of asset where assets producing something. And then we have wear out here, where components are worn out or something, we have replaced them to extend the life. So in the center part, that's what mostly we are concerned, or that's what where asset is operating, in producing what we want out of that asset. This is a better curve, Warble life curve. There was a Swedish scientist, Warble. He put together how reliability operates as a whole. This is a very complex formula here. However, as I said, the left side where infant mortality, if where it may be, short period of time, if we take that one out in our calculation power, and we are our right side, the center part, which is a design like constant failure rate, reliability is given to E to minus lambda T. Lambda is a failure rate, which is 1 over MTBF. So that's a kind is called Best-of curve for reliability. And this Weibull curve is used and also is performed to estimate asset life prediction, how much life is left on asset. For all for if, as I said, you take a right side and left side out of the equation, and this becomes very simple calculation, reliability equal lambda. T, which we use to calculate the reliability in our all the reliability analysis. As said, remember, reliability is given to E to lambda T, and where lambda is a failure rate on our MTBF, and T is a mission time, how long you want to operate this asset, and that's the way reliability is calculated. We're going to a couple of examples to clarify that more. Now, I just want to again so you understand. Always try to go for definition, what those mean. So think about reliability, what that means too. We talked about that earlier. Other term we're going to talk is maintainability and availability. What those mean to you. Okay. What reliability means to you, definition, maintainability to you, and availability. Write down and we're going to compare the notes. Okay. Reliability is a broad term focusing on asset ability to perform its intended function, as I said earlier, to support your operation, your manufacturing, provide a service or some other capability. Standard definition, Mail Standard 721C says it's a probability that an item will perform its intended function by a specified interval and under stated conditions. Understanding this term and how it differs from maintenance is key. Okay. As I said earlier, reliability is in a useful life period is given by E to lambda T, where lambda is failure rate, 1 over MTBF. Now, just remember, as MTBF goes up, your reliability will go up. Okay. As MTBF goes down, mean time between failure, reliability will go down. We should be taking a critical asset, and all the critical assets are like in this example, I'm showing one asset where we are trending mean time between failure data. You can take this every month, every quarter, year, whatever data is available to trend the data. So you see how MTBF you are working on your doing proper maintenance or redesigning some of the components, changing them. You can see as your MTBF going up. If it's going up, you're doing good. Remember that, okay? Maintainability is ease of maintenance. Again, it's a design attribute as well as how we train our technicians to repair. Do we provide them right training? Do we provide them right tools, work instructions, all those kind of things? Okay, and it's calculated by you taking the total repair time divided by number of failures. As I say, characterized by mean time to repair. Mean time to repair, some call it repair time, wrench time, whatever you want to call it. It's time to repair. Divided to sum of time to repair divided by number of failures. Again, in this case, it's lower the MTTR, better you are. You should be going down. Many times there is another term, mean downtime. And capture, many times we are using our CMMS systems or EM system to capture our data. And there we are really capturing when machine is down and when gets in operation. That time is called mean downtime. And repair time TTR in between because there's certain time, the delay time before start the repair, and mostly we try to ignore that part, but we need to know that to make improvements. We can talk a little bit more that's in the next couple of slides. Okay. Now, these are two slides on MTTR trending. A, where MTTR is going up, B, where MTR kind of took and then take a dive, went up and then took it high. Which curve, which A or B, which is doing better? This MTTR. So think in MTTR, meantime repair, we want going down. So B, machine B is doing better. That's the right way it's doing it. Okay. What's the difference between MDT and MTTR? And that's what I was trying to talk to you earlier. Let's take example here. Asset is operating at point SF. Start of failure happens. And it gets reported. And it takes a while, maybe 5 minutes, maybe 2 hours, to somebody start the repair. And RS period gets started. And then it takes again, they get the parts and get then at RC, repair gets completed and then takes few minutes, a couple of hours to clean up and all those kind of things, depending upon the type of machines. And then at BO, back to operation. So time between repair gets RS and RC's repair time, MTTR. Time between SF and BO, start of failure and back to operation is called mean downtime. And as difference is the delay before repair starts or before getting operation. And most of time, our CMMS system stamps repair time at SF. It's downtime, total downtime, but we call it MTTR. So keep that in mind that, hey, this is MTTR equal to MDT if there's no delays. And we need to know these delays, but most of the time we ignore these delays. We use MDT and TR same. Okay, that keep that in mind. But you have to we have to eliminate these delays somehow. You have to find what delays are. These are in our reporting system. We have to send people there in within 2 minutes, 5 minutes, 30 minutes, something. So those are kind of things we need to, those are administrative delays, could be management delays, whatever you want to call them. Availability is the function of reliability and maintainability. It's calculated by MTBF or MTBF plus MTTR or uptime or uptime plus downtime. So as I said, it's a function of reliability and maintainability. Okay. As a term, I'm going to throw you out which we should be aware. RAM score O are reliability, availability, maintainability, safety, sustainability, and operability. When we are designing an asset, we should be designing from RAM score O perspective. It should be reliable, should be easy to maintain, so it's high availability. We also should be safety, how we operate, safer to operate, and sustainability also. We should keep that in mind. It's energy efficient. We are using right kind of materials, sustainable materials, and easy to operate. So when we are designing an asset, it said we should be always thinking about ramp square hole. In fact, we should be specifying when we are buying assets based on RAM's principle, RAM's principles. Should be easy to operate, easy to support safety-wise, safer to operate, easy to operate, sustainable, easy to maintain, and it should be reliable, less failure as much as possible. So let's look into a reliability requirements to speak. This will give example how reliability is specified, how we should be using it. A plant air compressor was operated for 1,000 hours of last year. Plant CMMS system provides the following data. Operating time 1,000 hours, number of failures 10, and total hours to repair was 50 hours. What is the expected reliability the availability of this compressor if we have to operate this unit for 100 hours. We want to operate this unit for 100 hours continuously, and what's the reliability and availability of this? So we have MTBF, 1,000 hours of operation, divided by 10, 100 hours. Mean time repair is a 50 hours took to repair all those 10 failures. There were 10 failures, so 5 hours is the mean time repair. Now, as I showed you earlier, reliability is given to R2 E2 minus lambda t. If we put that number in this, like lambda is 1 over 100, t is 100. So if I put those there, it becomes 100 and cancel out, it becomes R2 minus 1. R2 minus 1, if you use a scientific calculator, you put 1, change the sign, and then hit e to power x, and you will get 0.37, 0.367. So that's a 37%. So what we're saying is, if we have a MTBF 100 hours and more want to run for 100 hours, and for a running for 10 hours of our mission time, we want to operate that machine, we are 37% reliable. There are 63% chances it's going to fail during the operation. Okay. Availability of this asset is mean time between failure, or mean time between failure plus MTTR, which is 100, or 100 plus 5, 95%. Okay, good. So far, good. I hope you understand that. Now, same example. What should be the MTBF value have to be if the reliability needed was 75% in order to meet the customer's expectation? What we're saying is, no, we got 37% reliability, and that's not acceptable. We want 75% or better. So what we need to recalculate our mean time between failure, as hey, need to upgrade those components with that MTBF. Now, based on B part of this is based on previous calculated MTBF value, what would be the MTTR if the availability needed was 99%? Okay, so let's look into this. We're going to use same formula. Okay, in this case, like here, I'm showing reliability is 0.7. We want 75% reliability. Now, E2 minus 1 or MTBFT, this formula. Now, if we put those numbers there, really have to natural log 0.75 T or MTBF. So our formula becomes MTBF equal to T time or natural log of 0.75. That's what I'm showing here. Okay. So this is what we are showing there. Let me, so this is what I'm showing you, that this MTBF is T over natural log of 0.75. So with that, your T is 100 hours, 1 over natural log of 0.75. And if you use that calculation, the MTBF becomes 347.6. And again, I'm going to recheck, making sure that's the same. I can go back R to equal 100 hour one new MTBF, and I get 75%. So now, what we say is to get 25% reliability, we need to improve MTBF from 100 to 347 hours. So we have to look in this machine what components are failure, what component we can replace with a hard reliable component. So we get a MTBF of 340, 350 hours, so to speak. Okay, that's what we have to do. Okay. Now, again, we want to know MTTR, new MTTR, or now MTBF is now going back to this calculation. So uh, MTTR comes to be 347.99 minus 347.8, 3.5. What we're saying is our new MTTR should be 3.5 to get availability of 99%. So to get 99% well, we need to have MTTR 3.5 hours. Okay. Now, when we're talking reliability, we need to understand reliability block diagram. All our machine, there are several components. Some of these components are in series. Some of these components may be in parallel arrangement. In series means if one component is down, the whole machine is down. Okay. And in a with the in parallel arrangement, if one component is down, machine can go a different route, go to pass through. So in case of reliability, in series, reliability goes down. Okay. In case of parallel arrangement, reliability goes up. So in series, you multiply reliability R1 times R2 in this example. In parallel arrangement, my reliability becomes Rm plus Rn minus Rm times Rn. This is just a two-part, two-component system. They'll be a little bit different if you have 3 or 4 or 5 components. Okay. Like this, I'm showing you a 3-component R11, R11. There are 3 components in this block. If I'm going to use 1 out of 3 all the time, only one, my reliability is 1 minus R cubed, and this becomes 0.992. If I need 2 out of 3, then my reliability 0.896, 89%. If I'm going to use all 3, then they kind of become in a series. If I'm going to use it out of 3, so it's a 51% is my reliability in this case. So you have to understand how they operate and draw the reliability block diagram. This is a table showing you a 4 in a system, 1 out of 2, 2 out of 2, or 1 out of 3, or 1 out of 4. So this came out from my Means Reliability Best Practice third edition book. So this is again, and you can refer to any reliability book, you can get it. And then there is software available also, which you can use to calculate reliability. Let's take an example here. I got this 4-component machine, R1, R2, R3, R4. R1, then I got 2 in a parallel arrangement, then I got R4. And these are their reliability, 0.9 and 0.8, R3, 0.8. So how to calculate this? So really what I have to do, I have to calculate this middle circuit, R2, R3 first, then put that number there, then they become a series, then calculate out. My next I have to calculate the center when I said center component becomes R2 plus R3 minus R2, R3, and that's 0.8 plus 0.8 minus 0.8 times 0.8, and so it's 0.96. So my reliability of this centerpiece of two component is 0.96. Now my equation becomes like this: 0.9, 0.96. So now I will multiply. So my reliability of whole system is, you have to multiply out of these 77.76%. That's my, so this system is 77.76. That's my reliability as whole. Okay. This, I will give you an example. These are 2 compressor systems. Okay. So X1 machine has these 7 components. Their reliability is given here. Their 40 hours operation 697, 693 is MTBF, and one is 97.8. My reliability of X1, there are 2 systems, as I said, X1 and X2. And X1 has reliability of 9772, X2 is 8545. Okay. Now, let's look into, this is kind of, I'm showing you all the components in both systems. So this is 99.7, this is 85.5. So challenge, the problem is here is these two systems, I'm showing you, 85% of the time we needed only one system to operate. When one system I need to meet my production need, only X1 or X2, I'm using one out of two, and my reliability is 99.67. Now, it's 15% of the time I need both systems to meet my production need. In that case, they become kind of a series. Now I have to multiply my reliability 83.5. Now, this is okay. 2 out of 2, 15% time, 83% is not good enough for our client, our customer. And our production people say, hey, that's not acceptable. They want better than that. So is we have to go back to this circuit like here, showing in the bottom here, and find which component, like in this case, electrical controls has a lower reliability of 83%. Now we have to work on this electrical controls, which component within electrical controls we can change to get the higher reliability. Now we can do that, and then we can go to next also, like this gear drive, 98%, how we can make it better than 98%. Okay? So again, you have to look each component in this series where you can work to make it more reliable. Okay, that's the way we improve the make more our asset more reliable. And when you're buying new component, you have to specify these kind of things. Hey, what reliability we are looking for, 80%, 90%, at what kind of operating conditions, as well as how many emission time, what's our emission time is, how we are to operate. Now, example here. I have these four systems. System one has a three component in series. System two has a four component uh, in some series, some parallel. System three has a six components in series and parallel arrangement. And again, system four is a little bit more complex. There are 6, 12 components in this case. Now, which system will be more reliable? And which system will be more expensive? Think about it. You have to calculate what's the reliability of this system is, what's the reliability of this system is, what's the reliability of using all this and that. And then again, depending on the components, how much they will cost you. What's your gut feeling? Which system will be more reliable? A, one, two, three, four. You know, if I think about it logically, system number four will be more reliable. Also, system number four will be much more cost to build. Let's look into this. Yes, system number one is 64.8% reliable. System two, four component, 77.8% reliable. Where system three is 87. Now, system four, boy, golly, I'm 99.6% reliable. But look how many components I have to use to get that. So now, yes, it's a lot more expensive too. 5, 6 times more expensive, but I can build it. Now, if I have to make better than that, I can change the components. I buy components which are more reliable, higher MTBF. That will improve the system reliability too. So I'm just showing you these examples that, hey, based on how their configuration is, these components, and how reliable their components with MTBF, and you can build system to meet your needs. In fact, you can build the whole plant, put a reliability black diagram, but you have to do you have to identify different scenario. In this case, I'm trying to show you there's a, a 6 compressors are sitting there. There are some coolers they use this plant uses. There's some heaters, And then these systems are valve, fuel system, electric controls, valves, and exhaust coolers. They, they are several of those. You have to put a scenario together, how many compressors you need to, how many of these machines to operate. You need a two, three, four, or you need all six. Same thing here. So based on your environment, how you're going to use your configuration, while you come up with several scenarios, then you calculate reliability of the whole plant. We had a challenge, my place where I was working. Our customer client was looking for, hey, tell us what's your reliability. It was not good when we started. But we showed them what's our reliability today, what will be 2 years from now when we put our capital prices together, or 5 years from now, or 8 years from now. We showed them how we are improving our reliability as we go. And that made them happy. And then they came to get to work with us and gave I mean gave us to do the testing and do their work in our place. We did fulfill all the requirements. Remember, improvements are change. Change is not easy to implement. What we try to do make improvement in our process. You have to talk to your people. You have to build the culture so they make the changes. People have been doing certain things certain way. They are happy with that. They are comfortable with those. And if we want them to change, do something different, we need to make sure there's a whiff on what's in it for them, why they should change. And that's what I found. Many times we try to bring new stuff, new change, make improvements, and improvements go wayside. People do it for a few weeks, then they go back to their old habits. So changing their habits, changing their behavior is very, very important. So you need to work on change management principles and change them. As Gandhi said, Mahatma Gandhi said, be the change you want to see in the world. You have to change. You have to show them why they should change. Same thing with you too. So in conclusion, organization exists to deliver value to their customers. All companies exist to deliver the value. If they won't deliver value, people won't come back. They won't buy our services, our parts, our products, whatever. Assets play a key role in delivering value. Assets have to operate defect-free, less failure, so they can deliver. Unreliable asset cannot deliver value. We need to make assets more reliable by specifying reliability requirements or improving reliability. You know, maybe just certain percent reliability for X hours of operation, a MTB of certain hours or MT of certain hours. These are kind of things we have to put in our requirements. Ensure training, upskilling of your workforce on a continuing basis by applying best practices and which will produce better results. Higher productivity, less failures, more uptime, safer operation, and it will reduce total cost of ownership. Try to understand how to specify reliability. What reliability you need also. That's another part. We need to work, hey, how reliable our assets should be. We don't want to, invest money if we don't need that reliability. Yes, certainly you have to make improvements and keep working on that. Okay. Some of the material, most of the material came out of Means Reliability Best Practice book and Uptime Dictionary and Standards of Asset Management. So look over these, hopefully these books, and also we have training available online, Means Reliability Best Practice training available online. You can go to Means ReliabilityX.com, get more information. This is my, usually I have time, but I don't have any question. Well, you can send me questions. We'll try to get you the answers. Uh, as I get it, I'll try to reply you back. So send me the questions or go to ask at reliabilityx.com or go to reliabilityx.com and get more information uh, about kind of training or right or services we provide. Uh, Hey, anytime, any question, just me a question. I'll try to help you out. Thank you very much. I hope you got something to help you in your workplace, your gamma, where you work, to help you out. Okay. Thank you very much. Take care.